Hello, I'm Jack Connolly, and I'd like to introduce Team 20's Project 3. So, Project 3 involved a request for proposal for a Mars cargo mobility system, or a macro, from a company that would like to develop these Mars rovers for future use in space projects. So, our job as Team 20 was to create a small scale prototype of this macro that will fulfill the needs of the space missions to come in the future. So, what we did was using a Raspberry Pi and some Lego components create a functional prototype for these future machines.
I'm going to start off the management of the team by talking about the sub-teams. The team was divided into two sub-teams, a hardware team and a software team. The requirement for the hardware team is experience with building and be mechanically minded. The hardware team needs to ensure the structural integrity and mechanical functionality of the macro. The software team is required to have experience with coding due to demanding nature of the codes. The software team is responsible for testing the sensors and programming the macro. Both sub-teams have independent meetings to design, build, and test their own parts of the macro. There are also team-wide meetings to resolve design conflicts between the sub-teams.
Thank you, Chenkai. This is Owen Johnson talking about the Gantt chart. We divided the tasks into hardware, software, and documentation. As Chenkai mentioned, we had two sub-teams with different strengths. Alex and Jack did mostly hardware, Brandon, Chenkai, and myself did most of the software tasks. We did have documentation tasks, but these were decided to be a team effort, and we would do them in meetings together. The timeline that you see here in this original Gantt chart was more ambitious than we expected. We spent more time on hardware than we expected, and we are currently spending the rest of our time in documentation. However, we were still able to get all our tasks done before the deadline so far.
Going on to the wheelbase design. First, we had to consider our overall design of the macro. How many wheels would we have? How would they be powered? How many of them would be powered? We originally had considered a differential steering four-wheel drive design. Both of the front wheels would be powered individually, and we would use the differential in the back to give extra power without compromising steering. This meant we would need a large wheelbase and a wide macro to do small, successful turns. After some consideration, I had the idea to do what is called a swerve drive in the front. This allows for the front wheel to be powered and be turned independently for accurate turns and the use of a differential or individually powered wheels in the back to assist with power. These pictures feature the entire wheelbase with the differential in view in the rear, as well as the gearing and motor usage for the swerve drive. We felt this allowed for a good balance between tight turns and power transmission. Through our testing, we saw our maximum turning angle was roughly 65 degrees reliably at maximum, while getting little to no slipping in the rear wheels. A few different considerations with our cargo design included the complexity of the design, how stressful it was on the components we were given to work with, and the size of the actual mechanism. A few ideas we started out with included a pusher off of a trailer. We also considered a hook that latched onto the cargo and released it, a dump truck style lifting bed, and our most ambitious design was a vertical trailer that would have moving supports on the bottom that held the cargo in place. Once in position to drop, the supports would rotate out from underneath the cargo, dropping it straight down directly into position. Most of these ideas were scrapped either due to complexity or being too large to be practical. This picture features our final design for the cargo mechanism. It was just large enough to fit the cylinder cargo, which was the largest at a 5-inch diameter base. This design includes a gate powered by the small motor in the rear, along with a ramp that was made and the retention arms to keep the cargo in the proper position. The cargo rests on the ramp, and when a drop-off location is detected, the arm rotates clockwise from this point of view, allowing the cargo to slide off the back of the macro and into the proper position. When the cargo ramp triggered, we had a 100% success rate with the cargo falling off of the ramp properly.
As is true of most engineering projects, our macro design went through many different iterations as we ran into issues along the way. So one of the biggest ones that we discovered early on was our idea of using 3 different independently powered wheels was deemed not possible because we did not have the available motor ports to also power the directional control on the swerve drive on the front wheel, as well as the cargo drop-off mechanism. So what we ended up doing was using a differential for our rear wheels. So we had 2 rear wheels powered by 1 motor. Also, we had to rework our back support structure to have a rigid enough cargo holding area so that our macro could hold the load of the simulated cargo.
This is Owen Johnson with software. Myself, Chenkai, and Brandon worked on software. You'll be hearing from them in a moment. We used 4 sensors: the light sensor, the line sensor, the Grove Pi Hall sensor, and the gyroscope. The light sensor was used to detect the line, and outputs were analyzed with and without a prototype ambient light shield, as you see in these 2 pictures at the top. The one on the bottom left is the final layout of the sensors, and the one on the right is a device used to measure ground sensor clearance. Our initial testing was to determine the sensor output type. The light sensor was analog, the line sensor was digital, the Grove Pi Hall sensor was digital, and the gyroscope was analog. The light sensor outputted various values. An example shown here, you can see it's significantly larger than the unhighlighted values where it's over a dark area. We used this difference to differentiate between a line and a no line. We also tested the Hall sensor on a magnetic beacon. We found that it could not detect the beacon past 1.5 centimeters. Software integration for the sensors. We had clean outputs ready for use with the line sensor, Hall sensor, and gyroscope. We can integrate those directly into our software. The light sensor outputted a darkness value. We needed to translate darkness into a decision about being on a line or not. So we decided on a cutoff value, somewhere in between the value over a line and the value over paper, and compared the light sensor value to that. You can see the flowchart on the right describing this function we made.
As far as line following goes, we decided to go with 3 sensors to ensure the macro knows its state at all times. We originally wanted to go with 3 line sensors, but the design was quickly ruled out due to the restrictions of Project 3. We decided to use the light sensor in place of the line sensor, which was tested to be the best alternative. In normal operation where the macro is perfectly on the line, it is expected that the line sensor detects the floor and the light sensor detects the line. The macro has 2 turning modes: the line following mode, which turns the macro 20 degrees to either direction, and the line finding mode, which turns the macro 50 degrees to either direction. The turning angle is calculated as a function of time to ensure smooth turning motion. The rear wheel speed is calculated with a cosine function to ensure they are slowed properly for turning. There are 2 cases that will cause the macro to turn left, both of which involves the left line sensor detecting a line. If only the left line sensor detects a line, line finding mode is entered to get macro back on the line. If both the left line sensor and the light sensor detect the line following mode is entered to keep the macro on the line. The same logic also applies to the right turns, as you can see in this diagram here. In case that no sensor detects a line, offline algorithm is activated. In this case, the macro will turn the front wheel 50 degrees to the direction it was turning towards. That way, if the macro is offline or on a broken line, it will still be able to hit the next line. Speed control during line following is achieved by calibrating the code with a modifier. A speed check script was written, and a 90 centimeter straight line was laid out. When the script is activated, the timer starts when the light sensor hits the straight line and stops when the light sensor stops detecting the line. The delta time and the length of the line are used to calibrate the code. The result is that when a speed in meters per second is entered, the wheels will spin at the correct degrees per second.
The ramp detection algorithm first waits for the gyroscope to initialize, because initially we had issues with the gyroscope waiting to actually give a value, and that caused crashing in our testing. Then it measures the base absolute angle of rotation, and this is each tick to see what the major change in the absolute angle of rotation is. And then we measure this difference from the previously updated base absolute angle of rotation. And we get a new angle from the gyroscope each tick, and then we obviously do that by this equation on the next slide, which is getting the difference between the base theta and the new theta each tick, and seeing if there's a big spike in the change, which is velocity at that point in a way. And if the difference is greater than 3 degrees, then we increase to 5 meters per second. And we did this because the robot would get stuck at the apex of the ramp, and of course the center of mass was misaligned, and this caused problems. And so we had to see the rate of change roughly to do this. And we used a small test ramp to do this. And our robot made it over this ramp, but it wasn't to scale, which we should have accounted for, which was an issue at the demonstration, unfortunately. And of course, here in this graph, we can see that resetting the base angle helps the accuracy, the success that it'll get over, and 3 degrees is a good value. User interface, we have an EV3 button, which takes input from the user. And if this button is pressed for 3 seconds and released for less than 3 seconds, it is counted as an incrementation for the mode. And the mode selects an external function to call. And this could be, for example, in the main demonstration track sequence or the speed test sequence. And if the button is held for more than 3 seconds, then it is a selection at that point. And here's a demonstration of that. Now, my philosophy for this is that the button was the easiest method. There's no other sensor that we would use. We didn't have super user access. We didn't use this because we would already be using our computers at the demonstration. And our user interface, whether it be the computer or the button, was obviously less than 90 seconds. That's quite a high value. We just hit run or we hold down the button for a number of seconds, but less than 90. And the cargo drop-off algorithm, we get a drop location. We see if the Hall sensor detects a magnet through a digital value stored as the number of hits. And if this is equal to the drop location, we slow down to 1 meters per second and change 30 degrees for 5 seconds. If the number of hits is equal to the drop location plus 1, then we stop the motors and drop for 3 seconds. And after this, we just continue on the line. And here's a demonstration of that. And then the philosophy for this is a timing sequence was added to be used because we were dropping 4 inches away, and that was a really bad thing. So we stopped, and we also decreased the speed so there wasn't a delay, and we got our accuracy down to a good number here.
With every design, there are good and bad aspects. Positives of our design included its tight turning radius, relatively compact design, the usage of many different techniques to achieve our goals, sturdy, well-built subsystems and chassis, and the advantage of having no wheel skid during turning. Negatives included the low ground clearance due to the maximum range of our sensors, especially our Hall sensor, the small room for error those sensors allowed, possible slipping of gears if we tried to turn too quickly or encountered too much resistance, and the complexity of our code to make everything function well.
So this entire project was centered around hardware and software, which would give us a final design. We had a hardware team with 2 people giving us swerve drive, rear differential wheels, cargo drop-off, and software team with 3 people that gave us line following, ramp detection, user interface, cargo drop-off, and obstacle avoidance. Now we had our shortcomings, which is complicated code in the beginning. We did add more comments later. We had a small room for error. We always had some sort of issue, like it going off the line or something like that, where there was a gap, and we didn't know why it would work one time and it wouldn't work another time, so it was really unreliable. And we could have fixed the jerking of it. We could have implemented a loss mode or the rate of hitting sides. For example, if it's on a turn, it's going to hit the line a lot more, and we're going to know we're on a turn, and we're going to increase the angle of turning. And the gyroscope, we could have used an angular acceleration instead of our own system, or an IMU, or an ultrasonic sensor, or we could have given the system more clearance, and we could have added suspension, remounted the sensors, or changed to have an axle in the front to raise up when the wheels go over. Or gears, they were always slipping, but we could have used a different mechanical design. There's always bad, but there's also good. And we had, as aforementioned, a tight turning radius. We had a really good design, a lot of potential in that design. It was only made out of Legos, but it functioned pretty well, actually. And if we got the code down really well, it probably would have succeeded. And we had good plans. We had a hill system. We were planning on the hill. We made our own little model for that. We had object avoidance, which we didn't use, and we crashed into a hill, or the cliff. And we had a linear algorithm. We had good plans, but only if we had more time, which is probably the biggest issue, is that we probably should have started really focusing on a bunch of different things at once instead of specific things. And we should have tested more. We should have utilized our time a lot better, and we didn't do that. But only if we had more time.